Hello everyone. Welcome to the second lecture of chapter 12 from class 12 physics, atoms. Okay, so it's under the unit 8, atoms and nuclei. So till yesterday we saw different kind of atomic or models for atoms that were given by previous scientists. Okay, like first of all, it was given by J.J. Thomson, the plum pudding model, and then Rutherford actually enhanced it and gave us a better understanding about the structure of the atoms, then Rutherford actually established that most of the positive charge or all of the positive charge actually is concentrated in the center of the atom in the nucleus, in the form of a nucleus, and the nucleus itself is actually making up majority of the mass of the atom. Okay, so this is what we learned yesterday. Then we also saw how this could have been proven by the experiment, the scattering experiment that was done by Geiger and Marsden, okay, on the suggestion of Rutherford. And we saw that how the scattering of the alpha particles while it is, projected onto a thin gold foil, either the particles got backscattered or they passed through or they scattered, but at high angle, okay. So these were the things that we saw. Then we stopped at atomic spectra. Okay, so what is atomic spectra? Just like a quick refresh. So all gases, okay, atomic gas or vapor for that matter, okay, when it is excited at low pressure, usually done by passing electric current through the gas itself, a radiation is emitted by such a gas, okay, and this emitted radiation will show a spectrum, okay, will show kind of signatures at certain specific wavelengths only. So such a spectrum is actually known as, as already mentioned yesterday in the last class, emission line spectrum. Okay, such a spectrum is called emission line spectrum. So usually what this is actually there is a dark band. Okay, this is a dark band. Over here we are showing the opposite. Okay, and the background is actually dark. Okay, and you have bright lines, okay, either closely spaced at one wavelength, then again spaced at different wavelength, then again at certain other wavelengths you'll find more lines. Okay, so this is actually how the emission line spectrum looks. As you can see over here also, this is the emission line spectrum for a hydrogen atom. Okay, so this is what is an atomic spectra. Okay, then we have spectral series. Okay, so what are spectral series? Is that at certain frequencies of light, okay, uh, by a particular element, okay, whichever element we talk about over here, if we just take hydrogen as an example, the uh, light or the radiation that is emitted by that element at certain specific wavelengths is actually characteristic of that element. Okay, so as you can see for hydrogen, okay, you can see that there is spacing between these, the sets of lines that are there. Okay, and each of them actually is characteristic of a specific wavelength. Okay, so this entire kind of a, what you, the way actually we saw in the previous diagram. Okay, actually this is the spectral series for the hydrogen atom. Okay, emission line spectrum, obviously these lines are actually at specific, and these are called emission line spectrum. And the entire, kind of along or through a series of wavelengths, okay, values, you can see that there are different series. Okay, and the entire spectrum that we get for hydrogen atom is actually called the spectral series. Okay, so this was actually first observed by Balmer. Okay, you can see over here one of the series is even named after him. Balmer series. Okay, so he understood the spectral series that is seen in the visible region of the hydrogen spectrum. What is a visible region? Okay, this actually the wavelengths between say 365 to 656. This is the only area that is visible to human eye. Okay, so this is called the visible region of the wavelength spectrum. Okay, and this was first noticed by Balmer. So this is called the Balmer series. Okay, so what he actually understood that the line with the longest wavelength, okay, so that would be 656.3 nanometer. Okay, so this one is actually this is corresponding to the color red. Okay, the color that we see. Okay, and this is actually the violet. If you remember, we have Vibgyor. Okay, so these are the different colors that we see in the visible region. Okay, so red is the longest wavelength and B has the shortest wavelength. Okay, when we are considering the visible region. Okay, so this is actually called the wavelength. Okay, that we see over here, that is actually H alpha. Okay, and then after that you have H beta. Then the third spectrum that we see at the wavelength of 434.1 nanometer is actually H gamma and so on. Okay, till you have H infinity, that is in the visible region itself, it will stop at the violet line. Okay, or the violet color. So as the wavelength is actually decreasing, okay, the lines, as you can see, the distance between the lines is actually decreasing. Okay, and we can say that it is getting weaker in intensity. Okay, the spectrum line, the line spectrum that we see over here. So if we see that, okay, then we can find or we can mathematically express the dependency of the wavelength, okay, with respect to the number of the integral values, okay, as 1 upon lambda is equals to r 1 by 2 square minus 1 by n square. Okay, your lambda is your wavelength. Okay, is your wavelength. R is called the Rydberg constant. Okay, this is Rydberg constant and its value is usually 1.097 into 10 raised to 7, okay, per meter. Okay, and your n can range from, you can have integral values like 3, 4, 5, etc. Okay, so this is how we can, this was actually given forth by Balmer. Okay, so this was given by, sorry, I'll just write here that this is the Balmer series. Okay, this is for H2 or, atom. Actually, no, this is actually H2, not on this side. That would become the gas then. Okay, so this is there. Now, this equation is also called as, since we are talking about the Balmer series and the empirical formula, this empirical formula is given by, Balmer himself. This is called the Balmer formula. Okay. So, if we, take your this as, suppose we take n as 3, okay, as per the equation. So, if n is equals to 3, 1 upon lambda is equals to 1.097 into 10 raised to 7. Okay, now you have 1 upon 2 square. Okay, your n is 3, so 3 square. Okay, so if you put all the, values and then you solve this, 1 by lambda will be equal to 1 by 1.522 into 10 raised to 6 per meter. Okay, so then wavelength, you take the reciprocal of this is actually 656.3 nanometer. Okay, now similarly, if you take, your n as equals to 4, okay, what you get, lambda will be for, corresponding to your, corresponding to, okay, so this will actually, the lambda will correspond to what we get for h beta. Okay, so similarly, if your n becomes infinity, we will reach the limit of the series. Okay, so that is actually this. Okay, so this is going to be n is equals to infinity. Okay, and if we consider this, okay, so this we found was 3, n is equals to 3. Okay, this was n is equals to 4. Okay, so this is how we get it. So similarly, we found this for Balmer series. Okay, so this I have already shown the Balmer series. Okay, so now if we try to find, there are other series also. Okay, like Lyman, Paschen, Bracket, and Fund. Okay, so let's just derive the empirical formulas for this in similar terms as we found. Okay, so Balmer we already found. What was the Balmer formula? 1 upon lambda is equals to R 1 by 2 square minus 1 by L square. Okay, now for Lyman series. Okay, for Lyman series, we have 1 by lambda is equals to R 1 upon N square minus 1 upon N square. Okay, over here, N actually ranges, starts from 2 and then goes 2, 3, 4. Okay, then you have another series called the Paschen series, Paschen or Paschen. Okay, so that is going to be 1 upon lambda is equals to R 1 upon 3 square minus 1 upon n square. Okay, from over here, this will start from 4, 5, 6. Okay, then you have the bracket series. So your bracket series is going to be 1 upon lambda is equals to R, okay, 1 upon n square minus 1 upon n square. Okay, and you can see progressively, you can see that the n actually, keeps changing. Okay, so as if you remember this one, okay, so Lyman is actually, which has the shorter or the shortest wavelengths in it. Okay, so over here the n starts from 2. Okay, then you have n starting from 3 in Balmer, then for Pascal your n starts from 4, then bracket. Okay, so as you can see that this is actually, the wavelength is actually going much higher. Okay, as we go down the different series. Okay, so then you have the fun series, fun. Okay, so that is actually 1 upon lambda is equals to R 1 upon 5 square minus n square. Okay, so over here your n will, as you can see that this is 5, so then there is a relation. Okay, so this is the relation over here. Okay, your Lyman series can also be called the, uh, it's actually in the, I'll just do in the next one. Okay, so your Lyman series actually falls in the ultraviolet region. Okay, ultraviolet region. So this is actually has the smallest wavelength. Okay, and your Pascal bracket and your fund series are actually in the infrared region. Okay, these are actually higher wavelengths. And then as we discussed, Balmer falls in the visible region of the wavelength spectrum. Okay, visible region. So now we saw that we could, get the different formula for different series in terms of the wavelength. Suppose we want to, write it in terms of frequency. So we know, okay, okay. So we know that the, speed of light is actually the multiplication of the frequency. This is the frequency into the lambda. Okay, or you can write it as 1 upon lambda is equals to mu by c. Okay, so then the Balmer formula that we had seen can be written as mu equals to rc 1 by 2 square minus 1 by n square. Okay, so this is how we can find the spectral series. Okay, and we can understand the spectrum for each of the elements. Okay, and this is usually how we can identify or try to understand the structure or the atomic structure of the elements. Okay, and at which wavelengths do they where the atoms will radiate or they will absorb the the radiation that is being that is there. Okay, so these are actually just empirical. Okay, and only certain frequencies are where we observe, not all. You cannot. There are a number of wavelengths, all the wavelengths over here. Okay, they sometimes don't have the required amount of information. Okay, next we go to the other model. Okay, this is the updated model. Okay, the model of the atom that was given by Rutherford actually is based on a lot of assumptions. One of them is that there is a central nucleus and revolving electrons, and the electrons revolving around the nucleus is kind of, stable. Okay, just like how our solar system is, sun-planet system. Okay, but there are some differences in the two situations that, the assumption that is being taken. Okay, so while we have an attraction force, okay, so the gravitational force is responsible for the planets to, to revolve around the sun. Okay, and the nucleus electron system over here that we had already considered, we had considered the Coulomb's law of force. Okay, for the electrons to be revolving around the atom, around the nucleus. Okay, so now we know that according to the classical electromagnetic theory, that an accelerating particle which is charged, okay, it can emit radiation in the form of electromagnetic waves. Okay, so we know this. Okay, and we also know that the energy of such an, suppose we are considering an electron for that matter, which is negatively charged. Okay, so the energy of such an accelerating particle over here, the electron, will continuously decrease, okay, as it is, and it will be spiraling inwards. Okay, and it should then, as per this theory, it should then fall into the nucleus. But we know that that is not how it is working. Okay, if that happens, then that atom cannot be called stable. Okay, so then this is a bit of a diversion from what we understand. Okay, about the kind of the path or the motion that we are considering for such a revolving electron. Okay, so another thing that we see in classical electromagnetic theory is that the frequency of the electromagnetic waves that will be emitted by such revolving electrons should be equal to the frequency of the revolution. Okay, so if the electrons are spiraling inwards, their angular velocities, okay, and their corresponding frequencies will keep on changing, and then the frequency of the light that is emitted because of this should also change. And thus we would say that there would be a continuous spectrum. Okay, there would be a continuous spectrum, which is not what we saw when we were considering the line spectrum. which we were just talking about. Okay, so this is why we can say that the Rutherford model, though it is very, very, valid, and it could be proven by some, the experiments and the spectrums. Okay, does not tell us the entire, truth or entire story of how the atomic structure is. Okay, so the next scientist, okay, or the people who were dealing with these things, okay, is Niels Bohr. Okay, then he tried to, understand the validity of the Rutherford's nuclear model. Okay, and then he said that actually it is valid. Okay, but the limitations that were there. Okay, so he tried to overcome those limitations. Okay, and he combined classical and early quantum concepts. Okay, and then he came up with his own theory, and then he gave it in the form of three postulates. Okay, so Bohr's first postulate stated that an electron is an atom. Okay, an electron in an atom could revolve in certain stable orbits without the emission of radiation energy. Okay, so this actually is the contradiction. Okay, this contradicts the electromagnetic theory that we had just seen. Okay, so I'm just writing it as EM theory. Okay, so this is actually a contradiction to the electromagnetic theory. So as per this postulate, each of the atom of in any element would have certain definite stable states, okay, in which it can exist. If it is not in those stable states, okay, then there will be the entire the stability goes, and then you can have the spiraling phenomena happening, but that does not happen. So each atom, okay, each atom has certain definite stable states. Okay, this is what is understood by this postulate of Bohr's theory. Okay, the second postulate then defines such stable states. Okay, so as per Bohr's second postulate, it states that the electron revolves around the nucleus only in those orbits for which the angular momentum is some integral multiple of h by 2p. Okay, so sorry, this is actually pi. Okay, where h is your Planck's constant. Okay, and so what Bohr's second postulate says, that electrons will revolve in orbits having an angular frequency, okay, suppose we call it L, having having angular frequency L as the integral multiple. Okay, so that would be n into the the factor that we had seen, 2 pi. Okay, so h is equal to 6.6 into 10 raised to minus 34 joule second. Okay, so this is the Planck's constant, and so we can say that the atom will be stable, okay, only when electrons in the atom are revolving in orbits, okay, which are considered stable only when they have an angular frequency that is an integral multiple of this factor. Okay, so this is Bohr's second postulate. So this is again defining the orbits in which the electrons should revolve around the nucleus. Okay, and now the Bohr's third postulate. Okay, this incorporates the atomic theory with the early quantum concepts. Okay, and the quantum concepts were actually given by Planck and Einstein. So he, utilized those. And what he stated is that an electron might make a transition from one of its specified non-radiating orbits to another of lower energy. Okay, so this means that electron can move between the orbits. Okay, with respect to the differences in their energies. Okay, and when it does so, a photon is emitted having energy equal to the energy difference between the initial and the final states. The frequency of such a photon, okay, then would be given by h mu is equals to ei minus ef. Okay, so energy of the initial state and energy in the final state. Okay, and this is again product of the Planck's constant and the frequency. Okay, so this is the frequency of the photon emitted. Okay, when electron move from one state to another. From these are stable states. Okay, from one state to another. Okay, so again, if we consider a hydrogen atom. Okay, hydrogen has the simplest atomic structure, so we are going to consider that. Then we can get the expression that will determine the energy of such energy states or the orbits that we are talking about. Okay, so we will again consider the r as the radius of such an orbit, radius of orbit. Okay, then we need to know the r. Okay, so then using Bohr's second postulate. Okay, we need to calculate r. So using Bohr's second postulate, we can find from the angular momentum. Okay, so L, that is the angular momentum, is equal to mvr. Okay, then suppose we have n number of such orbits. Okay, so then if we want to find the total angular momentum that is there, so ln is equals to m vn rn of the nth state. Okay, so that will be nh by 2 pi, and n actually varies. Okay, from say 1 to 3. Okay, and rn is the radius nth orbit, nth possible orbit. Okay, and Vn is actually the speed of the moving electron in the nth orbit. Okay, speed of electron in nth orbit. Okay, so this is what we get, and as we said that n can vary from 1 to 3. Okay, so then to understand the relation between v and r, okay, the speed and the radius of the orbit, we can get vn as equals to e by 4 pi epsilon 0 n r n. Okay, and then we get vn equal to 1 by n e square by 4 pi epsilon 0 1 upon h by 2 pi. And similarly, we can get Rn, which is actually equals to n square by m h by 2 pi. Okay, 4 pi epsilon 0 upon e square. Okay, so this is what we get. Okay. So this is what we are getting. Now this actually gives the speed, orbital speed in the nth orbit. Okay, this Vn will give that. Okay, and you can see that it falls by the factor. Okay, so it is the speed will decrease with increase in n. Okay, so in that sense, if we try to use, if we want to find out as per n is equals to 1, okay, so your R1 will be h square epsilon 0. Sorry, I just said h square. Okay, pi m e square. Okay, and your V1, okay, so you can find your V1 accordingly. Okay, so that will actually be e square upon, okay, you can cancel out your 2 pi and 4 pi actually. Okay, so what you are left with is 2h epsilon 0. Okay, and this R1 is actually called A0, which is also known as the Bohr radius. Okay, so this is what we get. If you then substitute the values for E0 and sorry, epsilon 0, H. Okay, if you get all these values over here, the mass of the electron, the charge of the electron, the Planck's constant, and the epsilon 0, then you can get the value of A0, which actually turns out to be 5.29 into 10 raised to minus 11 meter. Okay, so we can also, as per the radius of it, the variation of the radius, we can see that if your radius increases as the square of the integral that we are considering. Okay, now we understood, we got the radius, the Bohr radius, we got the radius of the orbital state, we also got the speed of the, the orbital speed related to that orbit. Okay, now if you want to find the energy of the electron, okay, so we want to find the energy of the electron, okay, the electron in stationary states. Okay, so it's not in the excited state, it's in the stationary state. Okay, we are considering hydrogen again over here. Okay, so if we consider hydrogen again, okay, then we can write En is equals to E square by epsilon 0. Okay, M by N square 2 pi H square and E square by 4 pi epsilon 0. Okay, so then this reduces to En is equals to M e raised to 4 8 N square epsilon 0 square H square. Okay, again, if you substitute for your M, for E, for H, and for epsilon 0, and at any particular N that we are going to consider, okay, so your En then reduces down to 2.18 into 10 raised to minus 18, okay, upon N square joules. Okay, so this is your atomic energy, okay. And since we are actually, we usually consider it in electron volts, okay, we don't consider it in joules. Joules is a very big unit, okay. So when we had learned this in one of the first unit 1 chapters, okay, 9 is equal to, so then your En then becomes negative 13.6 upon N square electron volts. Okay, so this is your energy of our atomic energy. Okay, the negative sign actually, what does it denote? It is showing that the total energy, okay, of the electron, total energy of electron moving in, okay, moving in an orbit means moving in an orbit is actually bound. We had already seen this, okay, previously also, even with the experiments that were done before Bohr's postulates, we had said that, we can say that the electrons are bound to the nucleus, okay. So this again is verified with even Bohr's model. Okay, so energy is needed to remove an electron from the hydrogen atom, okay, to a distance that would be considered very, very large from, with respect to the R of that electron or that orbit. Okay, so this is what we see from Bohr's postulate. Now, Bohr also, modified or enhanced the understanding of the atomic model. Okay, atomic model, and he gave us also the understanding of orbits and which orbits would be stable. Okay, now we come to the energy levels of the atom. So energy of an atom is said to be the least or has the largest negative value when the electron is revolving in an orbit very close to the nucleus. Okay, if this is your nucleus, okay, so the electron which is actually, closest to the nucleus will have the least energy. Okay, so for n is equals to 1, we'll have the least amount of energy. For as you increase the number of or you go away from the nucleus, the energy is going to get smaller and smaller. So the lowest state of the atom, okay, which is called the ground state, will be known as the state where it has the lowest energy. Okay, and the electron would be revolving in the smallest radius. Okay. Okay, I actually said the opposite. Okay, so as you increase or as you go farther away from the nucleus, the energy is going to increase. Okay, so larger energy will be seen in electrons which are in the outer orbits. Okay, so again, if you have the Bohr radius that is A0, the energy of this state is going to be the least that we already saw. Like if we use this expression, it will be minus 13.6 electron volts. Okay, so the minimum energy that would be required to free an electron from the ground state of the hydrogen atom would be 13.6 electron volts. Okay, so if you consider that, what does this mean is that if you want to excite the atom, okay, and you want to increase the or you want to shift it to the other energy state. Okay, so if you want to N2, okay, so if you want to remove an electron from from an orbit, the second orbit, the energy that we would require would be E2 is equals to minus 3.40 eV. Okay, similarly, then we can say that what is the energy required? We had seen this, okay, the frequency, okay, when we are trying to, push the electron from one state to another, okay, so that the energy difference can be found, okay, E1, it would be 10.2 EV. Okay, we already know E1, okay, and now we got E2, then we can put this in the formula and we can find it. Okay, and similarly for suppose we want to excite it to say E3, then E3 is suppose it is 1.51 electron volts. Okay, so again we are going to minus it. Okay, so the energy that is required will be, or the energy difference is going to be EV. Okay, so then this means that to excite the hydrogen atom from its ground state, that is n is equals to 1, to say n is equals to 3, we will need 12.09 electron volts of energy. Okay, and this you can find out for all different kinds of states. From the excited states, the electron can fall back to a state of lower energy also. And when it is falling back to say E1, okay, it will radiate that. Okay, so from E3, if it is falling to E1, that is a lower energy, where energy is low, okay, a photon would be released. A photon is released. Okay, so with respect to that, you can see that we can draw an energy level diagram. Okay, so this is the energy level diagram, and this is for the hydrogen atom. Okay, and the n for the n is given. This is your ground state, okay, where your energy is minus 13.6, and you can excite it to any of these levels. And when it falls back to n is equals to 1, a photon would be released. Okay, so this is what we understand as the energy levels. Okay, now we will see what is the line spectra of the hydrogen atom. Okay, we had already spoken about, kind of the emission line spectra. Now we will see as per the third postulate of Bohr's model. Okay, that is when an atom will make a transition from higher energy state with quantum number, where the photon is being, generated. Okay, so we remember that the photon's frequency can be given as, E n initial minus E n final. Okay, so initial is like the higher state, and your final over here, as you can see, NF is actually lower than the NI. So NI is going to be at the highest state. Okay, so if we then calculate it, it will be n e raised to 4 upon 8 epsilon 0 square h square. Okay, and then 1 upon n square the final minus 1 upon n square initial. Okay, or your VIF, okay, can be equal, okay, 8 epsilon squared HQ 1 upon n square F minus 1 upon NI square. Okay, so you can see this. Okay, and if we consider, the formula that we had found, with respect to the Ryder's formula, or the, Balmer's formula. Okay, Rydberg, with the Rydberg constant, you can see that, this can be given as 1 by lambda. Okay, this, and then this would be corresponding to that, and this would be, say, 1 2 square minus 1 n square, whatever. Okay, we can see the similarity. So then we can say that the Rydberg constant that we considered actually then can be computed using this these variables. Okay, so if you can try this out, if you put the values for n, the mass of the electron, the charge of the electron, the epsilon 0 value, and the Planck's constant, you can get this as 1.0. Sorry, this would be 3 into 10 raised to 7 per meter. Okay, and for the, this is actually very close to the value that we had got in the Balmer formula. Okay, so this is actually called the Rydberg formula. Okay, and it has similarities with the Balmer formula that we had found. Okay, for the Balmer series. And so the Rydberg constant can be defined as this value. Okay, which is close. So there is an agreement with the theoretical and the experimental value of the Rydberg constant. Okay, and this actually gives us the validation of the Bohr's model. Okay, so we saw this. Now suppose you have, NF is equals to 1. Okay, your final is 1, and your NI could be any of these. Okay, and then suppose your NF, if you're considering NF as your as 3, then all the NIs have to be higher than 3. Okay, so this is, then we can get at that for each series, okay, that each limit of the series, okay, what would be the excited states, and what would be the amount of energy that is actually, brought about for, at different, wavelengths at different frequencies. Okay, so the result from the such Bohr's model is actually the presence of the series. Okay, so all the series that we had understood from the the line spectra, okay, it also holds good when we are considering the Bohr's model. So we can say that Bohr's model is, kind of very close to the, so it's very similar, or it has close approximation to the Rutherford's model. So Rutherford's model is valid, and Bohr's model actually, enhances it, the understanding of it. Okay, so the various lines in such atomic spectra are actually produced when, the states are jumping. Okay, from a high energy state to a low energy state. And then the photons are emitted, as we had already said. And these spectral lines are actually called the emission lines. Okay, that's why we also find the emission line spectrum. Okay, but if the photon is absorbing, if the atom is absorbing the photon that is being, produced, okay, which has the same energy as that was needed by the electron to get excited to the higher energy state. Okay, the process is then called absorption. So if photons with, if we write, the photon is absorbed, okay, and the energy of the photon is actually equal to the energy of the, say, going from a lower state to a higher state. Okay, so the photon is absorbed at that time. Okay, because it requires that energy to get, to excited. So if the photons there is a continuous range of frequencies, okay, that is, passed through a rarefied gas. Okay, and if you use a spectrometer to understand it, these absorption bands, or these, frequencies where the absorption is taking place, will actually show you dark lines, okay, in that continuous spectrum. These dark lines are actually the frequencies that are absorbed by the atoms of the gas, and we can say that these are again characteristic of each of the elements that are actually producing such spectrums. Okay, so we have another, explanation or a hypothesis that is called the de Broglie's hypothesis. This was, kind of experimentally verified by scientists called C.J. Davison and L.H. Germer, okay, in the later on. So what the second postulate of Bohr's model, stated that, the electrons would be orbiting around the nucleus in, states or in orbits which have the angular, frequency as Ln is equals to nh2 pi. Okay, Ln is equals to nh2 pi, where your n can vary from 1, 2, 3, and so on. Okay, so we know this. So why are we considering the angular moment to have only those values which are integral multiple? Okay, so this was what was given by Louis de Broglie. Okay, and he argued that the electron in its circular orbit, as it was given by Bohr, it should be visualized as a particle wave. Okay, so if we get in the, kind of, particle wave, then we can, understand it in the terms of wavelengths. So if suppose like when a string is plucked, okay, a vast number of wavelengths are excited, but only those wavelengths will survive, okay, which have the nodes at the ends and form the standing wave of the string. Okay, so this is again coming under the, wave theory of it. So waves with the other wavelengths, okay, which are not, having the nodes at the ends and not forming the standing wave, will actually interfere among themselves, okay, and their amplitudes will become zero because they're interfering. Okay, so suppose you have an electron, okay, you have an electron moving in the nth orbit. Okay, so we are going to consider the nth circular orbit. Okay, so that would be Rn. Okay, and the total distance, then the circumference would be 2 pi Rn. Okay, and that would be equal to n into lambda. Okay, so, and n goes from, goes from 1, 2, 3. So this actually, kind of gives you that understanding of the standing waves. You can see the nodes are at the ends, and this is the standing, wave, and this is the wavelength of one of the wave, okay, that we are considering. So you can see that the circumference of the orbit is actually the integral of the wavelength, okay, that we are considering. So if your orbit is, if you are considering the fourth orbit, okay, where your n is equals to 4, so your circumference for that would be 4 lambda. Okay, where lambda is actually the Broglie wavelength. Okay, so this is what we can understand. Okay, and this is the way the electron is going to move in the nth orbit. So we also know that lambda is a function of the Planck's constant and p. Okay, where your p is your momentum, magnitude of the momentum of the electron. Okay, so if we consider that, if we consider the momentum now, so the above equation can be then given as, you know, where h will actually become, sorry, the wavelength is going to become h by mvn. Okay, because the momentum is actually the product of the mass of and the speed. Okay, so then finally your expression then becomes n h by mvn, okay, or mvn rn is equals to nh by 2 pi. Okay, so this is again the quantum condition, okay, that was proposed by Bohr for the angular momentum of the electron. Okay, so this is similar to the second postulate, okay, where we were saying, so the angular momentum is the integral of h by 2 pi. Okay, so then we can say, you know, there are a few inferences that we can make after all this, okay, that the Bohr's model, which involved actually the de Broglie hypothesis, okay, it gives us an explanation of the Bohr's second postulate. Okay, so every postulate of Bohr can be, you know, uh, it can be explained, it can be justified, and it has been justified by different, you know, scientists by experiments or by considering other theories. Okay, so we can quantize from this that the angular, you know, the angular momentum of the orbit where the electron is orbiting has to be an integral multiple of the Planck's constant divided by 2 pi. Okay, so the Bohr's model, which involves the classical trajectory picture, okay, where we are considering that, you know, the sun, moon, the solar system kind of, you know, understanding where this is plus and this is minus, or the minus electrons are, you know, in stable orbits. Okay, so when we consider this, okay, uh, this is again a validation of Rutherford's model also, but there are few limitations. Okay, so if we consider the limitations of Bohr's model, okay, so one of the first limitation is that Bohr's model is, though it is applicable to hydrogen atoms, okay, it cannot just extend to 2 electrons in atoms like helium. Okay, and analysis of atoms with more than 1 electron, you know, kind of it was tried on the lines of the Bohr's model, but it did not meet any success. So one of the limitations is Bohr's model is applicable to hydrogenic atoms. Okay, for all other atoms, it's difficult, and because the electrons which are there not only interact with the positively charged nucleus but also with other electrons. Okay, as we know, you know, later on or then there are valence electrons. Okay, they can jump from one atom to another, they can form ions. Okay, so this cannot be very easily explained using the Bohr model. Okay, Also, the formulation of Bohr model involves electrical force between the positively charged nucleus and electron, and but it does not include the forces, electrical forces that are between, uh, electrons, which actually appears, when you consider multi-electron. If there is only hydrogen we are considering, we can only, appreciate the electrical force between the positively charged nucleus and the electron. But in suppose atoms which have multiple electrons, it does not consider the electrical forces between the electrons themselves. Okay, so that is why it is only applicable to hydrogenic atom. The next limitation is actually that the Bohr's model correctly predicts the frequency of light emitted by hydrogen atoms only. Okay, but the model is again unable to explain the relative intensities of frequencies in the spectrum. Okay, so it can predict, okay, so we can say Bohr's model can predict the frequencies of light emitted by H or hydrogen atom, okay, but unable to explain the relative intensities, okay, the relative intensities of the frequencies in the spectrum. Okay, like we could say that some of them had weaker frequencies, okay, but Bohr's model could not explain the, the circumstances of the, reason behind those, okay, in the spectrum. So as we have seen that in the emission spectrum, okay, some visible frequencies will have weaker intensity. We do not know why. Okay, experimental observations, try to understand this transition, and the transition of the, electrons when they are, shifting, or when they are, kind of excited, that is considered. But Bohr's model itself is not able to, express this. So the conclusion is that the Bohr's model gives a very nice, elegant, visualization of an atom, and it cannot be, generalized, or it cannot be applicable to complex atoms. So for complex atoms, okay, we need to use other theories, okay, so which are actually based on quantum mechanics, and they will actually give you a better picture. So this ends our, chapter 12. Okay, so hope to see you in that.